Welcome everyone. Today, we'll dive into computing square-free numbers and explore the fascinating application of the Möbius function together. Last time we proved that the Möbius function is multiplicative. Now we will see how it helps us count square-free numbers. Recall that mu of n is a multiplicative function on positive integers. The signs of mu of n reflect the principle of inclusion, exclusion. Now, let's tackle a new question. How many square-free numbers are there less than or equal to 1,000? Our goal today is to turn these ideas into an explicit recipe for computing Q of 1,000. Before any formulas, we need a crisp picture of what square-free numbers are. Definition: a number n is square-free if no prime square, like p squared, divides n. Examples: 1, 2, 3, 5, 6, 7, 10, 11, 13, 14, 15. Non-examples: 4, 8, 9, 12, 18, as they contain some p squared factor. So square-free just means that in the prime factorization, you never see a prime repeated twice or more. Now let us turn that definition into a counting problem using inclusion, exclusion. For n to be square-free, it must not be divisible by 4, 9, 25, 49, and so on. Think about the sets. Multiples of 4, multiples of 9, multiples of 25, multiples of 49, and so on. Count the integers less than or equal to x that are not in any of these sets. This plus-minus pattern from inclusion-exclusion is exactly what the Möbius function will encode for us. Here is the compact formula that Möbius gives us for counting square-free numbers. We sum over all positive integers d, whose square is at most x. For each d, we take mu of d times the number of multiples of d squared up to x, given by the floor of x over d squared. The values of mu decide whether we add, subtract, or ignore those multiples, reproducing exactly the inclusion-exclusion pattern over prime squares. Sum over all d, where d squared is less than or equal to x. Mu of d is 1 when it is the product of an even number of distinct primes. Mu of d is -1 when it is the product of an odd number of distinct primes. Mu of d is 0 when d has any square prime factor. This is our main tool. Plug in a value of x, and this sum will tell us exactly how many square-free numbers live up to x. Let us see the formula in action for x equal to 100. List d with d squared less than or equal to 100, ranging from 1 to 10. Table columns include d, d squared, mu of d, the floor of 100 divided by d squared, and the contribution. 0 rows are when d equals 4, 8, or 9, since mu of d is 0. Add the contributions to find Q of 100. Here we have one term for each d from 1 to 10. The terms with d equal to 4, 8, and 9 vanish because mu is 0 there, and the remaining terms add up to 61.
So out of the first 100 integers, exactly 61 are square-free according to this calculation.
We could check this by listing all numbers up to 100 and deleting the ones with square factors, but the Möbius method got us there systematically. Now we push the same method to larger values of x. For Q of 500, d squared is less than or equal to 500, so d is between 1 and 22. For Q of 1000, d squared is less than or equal to 1000, so d is between 1 and 31. Same table idea. Use calculator or code for speed. Computed values. Q of 100 equals 61. Q of 500 equals 304. And Q of 1000 equals 608. When we divide each count by x, the proportions are all sitting around 0.608, already quite close to a common value. Even with these relatively small values of x, we see a hint that the fraction of numbers that are square-free is settling down to a specific constant. The numerical pattern we just saw is not a coincidence. It reflects a deep theorem. As x grows without bound, The fraction of numbers up to x that are square free approaches a constant equal to 6 divided by pi squared, about 0.6079. Behind the scenes, this density comes from an identity for an infinite series involving mu of d over d squared, which turns out to equal 1 over zeta of 2, and that simplifies to 6 over pi squared. Empirical. Q of x over x is near 0.608 for x equals 100, 500, and 1000. Exact constant. 6 over pi squared is approximately 0.6079. Identity. The series with mu of d over d squared equals 1 over zeta of 2. We will spend later lectures explaining why mu connects to the zeta function and where this beautiful constant really comes from. Let us gather the main ideas before we move on to the algebraic machinery behind them. Mu of d encodes inclusion-exclusion over prime squares. The formula for q of x uses multiples of d squared weighted by mu of d. Concrete results. Q of 100 equals 61, Q of 500 equals 304, and Q of 1000 equals 608. Square-free density tends to the constant 6 over pi squared. In the next lectures, we will set up Dirichlet convolution, which turns the Möbius function into a precise inverse for certain arithmetic sums. Let us finish with a quick check that you can drive the formula yourself on a small example. For x equal to 50, the formula looks just like before, but the sum only runs over d with d squared at most 50. Using symbols, express q of 50 inches terms of mu of d and the floor of 50 divided by d squared. To find q of 50, list all d values where d squared is less than or equal to 50. Try to keep both the symbolic formula and the intuition about avoiding square factors in your head as we move toward more abstract tools.